Oh, all right. Welcome. I hope you logged in today, and as you're logging in, you're thinking, man, I hope Mr. Metcalfe gives us 2 scoops of logic and reasoning today. Because if you did, boy, it is your lucky day, man. We are going to knock out 2 short lessons. We're going to start off with Unit 2, Section 3, and then I'm just going to roll right into Section 4. I'll tell you when that is happening. I've also on Google Classroom, I've provided you with guided notes for both lessons. They should be on there. It'll save you a little bit of writing. I'm realizing this second one, there's some problems at the bottom of the guided notes that are not on these screens. So you might want to pull up these if you don't have them. If you can have another window open, have these questions, because at the end of the first lesson, I'm going to just ask some questions right off the back of here. But man, I hope you are ready to go. I am. I've got my agua here. Because I might need it. We're going to let's jump right in. Quick reminder, we're on pace to have our Unit 2 test, not this Friday, but like next Friday. And you're saying, well, isn't that an e-learning day? The morning, yes, it's an e-learning day. I think we're going to have everybody, the in-person students and the online students. I think everybody's just going to take it online that day. See if we can blow up the servers. Well, I don't even blow up like bomb or anything. Just just overload them. See if they can handle all 173 of you all taking a test in the same morning. So just put that on your radar. I think that's September 4th. It is an e-learning day. We're just going to have everybody take the test online on that day. All right, let's go. So today we're going to talk about good definitions and biconditionals. And some of y'all think, didn't we already learn about biconditionals? We learned about conditionals. Biconditionals, as you know from words like bisect and bicycle, bi means two or both, all right? So and we'll talk more about that at the end of the lesson. So first thing we got a definition of good definition. So right up here, if you got the guided notes, here's a spot for good definition. You just write that definition right there. Boom. A good definition is basically a statement that can help you identify or classify an object or objects, right? So if you have a good definition of something, what it is, then you can use that definition to classify things. And that's kind of what we're going to do a little bit today. And I've made up I made up a fun word, and then your math books made up a couple of fun words. And we're going to, even though they're not even real words, we're going to, based on some examples, we're going to be able to figure out what the definition is. Now, I'm not going to lie, this first lesson works better with students in class. So I've brought some fake people together to give me some fake answers for this next thing. And I'm going to kind of use answers that the actual real students gave to this to just sort of help you see the process. All right? So here we go. What we're going to do is we're going to look at this fake word. And this fake word is beast mode. All right? You all have probably heard people say beast mode before. We're going to pretend like it's a totally fake word. So put out of your head what you think the word beast mode is. We're going to say it's a brand new fictitious word. And here are some examples of things that I think are beast mode. We got Clint Eastwood. We got Arnold Schwarzenegger. We got Bruce Willis, Daniel Craig, Sylvester Stallone. And I know I'm old, so a lot of my references are old. I tried to think of some younger references. I think most people know these people. Not too many people were familiar with this Daniel Craig guy. I'll talk about him in just a moment. But here's some examples of things that are not beast mode, like that Robert Pattinson. And I thought everybody would know him, but a lot of people said they didn't know him. He's one of those sparkly vampire guys in, what's that Twilight thing? He's one of the main sparkle ones. And then this Daniel Radcliffe, this one blew my mind because I'm sorry if some of y'all are going to be like, I'm shutting this guy down right now because of what he's about to say. I'm not a Harry Potter guy, but I know Daniel Radcliffe is Harry Potter, so that's the Harry Potter guy. And then there's Vin Diesel, and then there's this kid. I don't know his name, but he's in those little wimpy kid movies. These are examples of not beast mode. So you look at those, and then you look at these, and since, like I said, I'm old, and some of these references are old. Clint Eastwood, he's known as Dirty Harry. He's one of those like guys who like doesn't mess around. He's one of my favorite actors, but he is really old now. And then everybody knows who Arnold is. And Bruce Willis, I'm thinking about him in that movie Die Hard. And then there's Daniel Craig. You might not know that. He's the James Bond 007 guy, the probably most current one. And then Sylvester Stallone. If you don't know him, you need to, because he's one of these rare individuals. There are certain characters in cinematic history that everybody just should know, and rarely does an actor get to portray two of them, and he does. One of them, I think he literally created himself, and that is the character of Rocky, the famous boxer, fictitious famous boxer, Rocky. And then he's also portrays Rambo, the guy who just goes, ex-military guy who just goes in and takes care of business when business needs to be handled. So Sylvester Stallone, you just need, and he's in other movies too. Some of these guys, I think multiples are in the movie Expendables and stuff like that. So you probably are familiar with him and some others. But so that's beast mode. These are not beast mode. So what I did today is I had my students looking at these examples and non-examples, come up with what they thought were the definition of beast mode. So some of them said old dudes. All right, beast mode must mean old dudes. Well, I didn't want to go by age. It did so turn out that these guys are kind of older people than these, but that's not what the definition was. And if you want to pause it here and think about what you think beast mode might mean, I'll give you a chance to do that. Okay, welcome back. I hope you thought about some of these guys. Maybe you did a Google search and saw some of the movies they were in, or whatever. And don't watch some of those movies if they're rated R. Don't watch them, and because unless your parents say it's okay. I don't want anybody to watch any movies that's not in your age appropriateness. All right. So I mean, this wimpy kid movie and these Harry Potter things, I would assume they're okay to watch because they're just I don't know what they're doing in these movies. Something about a kid with glasses and casting spells and stuff. And this movie's pretty good for everybody. I've even watched that. My kids like that. Okay, so another thing some people said was, well, these dudes over here are all like big and buff and stuff like that. They were using some of that kind of language as the definition. And then I said, well, some people think this Vin Diesel guy is buff. And they're like, yeah, they do. So why would he be over there? And then when that hint came up, then some other people said, well, then I made the comment as like, well, I really like these guys. And for some reason, I don't have anything against Vin Diesel, but he's not like, I don't really like his movies or whatever. So then some people started saying, okay, these are actors that Mr. Metcalfe likes, okay? And that's true. I do like all these guys, and these not as much. I mean, I don't have anything against them. I don't have anything personal against them or anything like that, but they're not my favorites. So so that was getting closer. So we're getting warmer when we start saying actors that Mr. Metcalfe really likes. And then somebody said, oh, okay, well, what about, we said about buff and tough and all that kind of stuff. So then somebody finally, after about 10 or so guesses, finally somebody came up with the definition of these are action heroes that Mr. Metcalfe likes. And that would be true. That's pretty much the definition of beast mode. Action actors who are action heroes that Mr. Metcalfe likes. Now, he's an action hero too, probably. I just don't particularly like him or his movies, and so that's why he's not beast mode. So part of the definition is something that Mr. Metcalfe likes, and so that's part of it. So our final definition for beast mode, if you want to write this down, beast mode would be, oops, I'm in the wrong zone here. We'll put this right here. Beast mode means actors that Mr. Metcalfe likes, that Mr. M likes, that portray action heroes. I think one class said tough guys. Uh-oh, is that going off? Am I going off the screen a little bit? Let me adjust. Yeah, I don't want to go off the screen because that would be bad. So it looks like you all can see that now. So one class said they didn't say action heroes; they said tough guys. That's close enough. So pretty good definition there. So there's parts of it. It's got to be ones that Mr. M likes. They got to be action heroes, and they're all actors. All right. So that's the elements of that good definition. So that was just a little way to introduce you to coming up with good definitions based on looking at examples and non-examples. All right. Okay, let's move on. Here's the 3 components of a good definition, and there's a spot for that. Oh, here's a spot for you to put the beast mode in the definition right here. And then in your guided notes, here's the 3 components of a good definition. You want to use clearly understood terms, meaning terms that we're all pretty familiar with, like, and you don't want to use slang, all right? Some people were using slang in their answers. I forgot what they said, but we'll just don't use slang. Clearly understood terms. You don't want to use big, really fancy words, like if you're trying to define something and you use other words that people don't even understand because they're so big and fancy. Yeah, that's not helping anybody. So you want to use clearly understood terms that explain it kind of correctly, but also simply. All right, and then be precise. Some people were saying stuff like just, macho actors. That was one that came up. Someone said those guys were macho actors. Okay, that's sort of right, but it's not precise enough because somebody would say, hey, well, that Vin Diesel guy, he's a macho actor or whatever. So you want your definitions to be precise. Now here's the last one, and the one we're really going to focus on today. The definition needs to be reversible. All right. Now what does that mean? Well, we've been talking about conditional statements where we say, if blah, 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 then blah, blah, blah. That means, can you do that with your definition and reverse it and it still be correct? So if you go back to beast mode, you could say it like this. If someone is beast mode, then they are an actor Mr. Metcalfe likes that portrays an action hero. Now, if I do the flip of that, which hopefully everybody knows is called the blank converse, it would be if it's an actor that Mr. Metcalfe likes that portrays an action hero, then they're beast mode. All right? See how I reversed that if-then statement? I kind of reversed the definition. If it works doing that, then you've got a pretty good definition on your hands if it's reversible. And we're going to come back to that in just a minute. All right. So, again, pause when necessary because I'm moving along because we got 2 juicy lessons today. Okay. Now, if you don't have your guided notes, you'll want to pull them up. If you didn't print them out, I know some might not have that option. But if you don't have them, you're probably going to need to pull up this from the Google Classroom and look at it because we're going to be talking about some stuff on here. And we're going to be talking about another fake word called polyglobs. And on your thing, I'll hold it up close. I don't know if you can see that very well at home. We got some guys that are polyglobs up here, and then some guys underneath them that are not polyglobs. And then we got a bunch of wannabes over here. And that's probably going to be really hard for you to see at home. So I hope you have pulled this up on your computer or printed it out. There's 3. There's A, we'll call him Alan, I guess. And B, we'll call him Bob. and C, well, of course, we'll call Charlie. They're here, A, B, and C. And first you need to look at these characteristics of these guys that are polyglobs. What do they all have in common? And then look at these guys that are not polyglobs. All right, so I'll give you a chance to do that. You can hit pause, look over this sheet for a few seconds, pull it up if you need to pause the video and go to it, look at them, but decide if you think A is a polyglob, B is a polyglob, and C is a polyglob, and then be prepared to be amazed by the answers, all right? All right, welcome back. So let's look at A. Now, A, I hope your photocopy is pretty good, but A is not a polyglob. A is not, because if you look over here at the polyglobs, they all have 3 eyes, and A, he has only got 2 eyes, so he is not a polyglob. All right, hopefully everybody had no for that first one. How about B? Now you look at B, okay, so he's got the 3 eyes, so he looks good, but we better check other factors. I noticed the polyglobs, they all have 3 tentacles, or as some of my students were calling them, legs. And so does Bob over here, B. He's got 3 legs, tentacles, and 3 eyes, so yes. I hope everybody had yes for B. That is a polyglob. And then C, all right, let's look at him. He's the one that's down underneath the octopus. He would not be a polyglob. Hopefully everybody had no for that one. And the reason on that is he's only got 2 tentacles, and all the polyglobs over here have 3 tentacles. All right. So before we move on to an actual definition of polyglob, that's what we're going to come up with in a minute. I was looking at the non-polyglobs, and depending on how well your guided notes photocopied, I hope they did, the middle one. Some students have been pointing out today, hey, the guy in the middle, he's got 3 tentacles and 3 eyes. Why is he in the non-polyglob section? Well, look at his eyes really closely. And if you do, and your photocopy is not that jacked up, you'll notice he has 3 white eyes. And all the ones that are in the polyglob section, they all have dark eyes. So having white eyes kicks you out of the polyglob club. So you got to keep that in mind when you're coming up with your definition. So just to speed things along, our best definition, they use the fact that this is underwater, and you got octopus, you got a fish, you got a seahorse, so this is probably the ocean. So some people said, called a polyglob, they said it was a sea creature, which I like. I think that is kind of important to what a polyglob is, according to this picture. It's a sea creature with 3 dark eyes. It has to be dark eyes. It can't be white. And 3 tentacles. Tentacles. Hopefully I spelled that right. I think I did. And I think that was it. Yep. That was a pretty good definition of a polyglob. It's a sea creature. We incorporated that it has to have 3 dark eyes and 3 tentacles. So hopefully you got that. And then we moved down. Now hopefully it got cut off on some people's guided notes, but they got the word biconditional. So here we go on biconditional. Bi, as you know, means 2 or both. All right. So biconditional means we're going to take 2 conditionals and kind of jam them into one. But it only can be done if the original conditional is true and its converse is also true. Now that's difficult to come up with sometimes. Like I could say if my name is Scarlett Johansson, then I'm in Mr. Metcalfe's class, right? Well, that would, if we're pretending like she's in my class, that would be true. But when I reverse that, or I do the converse of that, and I said, if I'm in Mr. Metcalfe's class, then my name is Scarlett Johansson, that's not true. She would only be one student. I have a ton of other students whose name is not Scarlett Johansson. So sometimes it's hard to find one that's true, frontwards, and then the converse is also true. But if you do find one that works, and good definitions do work, then you can make a biconditional out of it. I'll show you what I mean. Okay, so hopefully you can see that at home. It's small. It's actually not on the guided notes. I forgot about this. I added this one on guided note. People, we're adding this right underneath the definition of biconditional. It says ScarJo example, so you put that right there. So we've got, if you are the Scarlett Johansson, not just a random Scarlett Johansson, the Scarlett Johansson, then you play the Black Widow in the Avengers movie. So I'll pause, you can pause if you need to copy that down because it is not on your guided notes, and I apologize. These lessons, like I said, they're kind of designed for you to be in person. I'm trying to adapt them for you online people. I don't want you to miss out on anything, and you're not. You're not missing out on anything. The home people or the in-person people are getting the same thing you're getting. So, is that a true statement? Well, if you're not familiar with the Avenger movies or Scarlett Johansson, you might not know this, but it is true. She portrays the Black Widow in all the Avengers movies, so we're going to write a big fat true right here. And I can feel my pen is getting out of calibration. I'm going to try not to let it bother me. So that's true. Now, we want to write the converse of that. Now, hopefully you picked up when you watched the videos the other day. Converse is when you take what's called the hypothesis, all this stuff after the word if, and you switch it with the conclusion, which is all the stuff after the word then. All right? You switch those two pieces, so the converse would be if you play the Black Widow in the Avengers movies, play, and to speed up, I'm going to say the BW. Hopefully everybody knows that's Black Widow. If you play the BW in the, I'm going to say Aven movies, comma, then you are the Scarlett Johansson. Then you are the, and we'll just call her ScarJo because I've heard she doesn't really like to be called that, but she'll understand to save time. You are the ScarJo. Okay, what's the truth value now of the converse? Boom! It's also true, isn't it? If you play the Black Widow in the Avengers movies, then you are the Scarlett Johansson. Yeah, that's right. So far that I know of, she's the only one who's played the Black Widow. All right, so now, here comes the new part. How to write this, and again, I apologize for my cursive. I'm not very good at cursive. And sometimes when a word is really long, like biconditional, I slip into cursive halfway through. So this says biconditional format. Okay, here's how you write a biconditional. Now remember, bi means two or both, which means it's true both ways. We just talked about it. The original was true. The converse is true. So it doesn't matter if you want to go in the order of the original or if you want to go in the order of the converse. Either one is fine. So you need to know that because on a multiple choice test, they might have gone with the original order or they might have gone with the converse order. Either one's okay. So you gotta know either order works. Now, what happens in biconditional format, I'm going to tell you, make a little cheat sheet for you. You don't write if at the front. Don't write if at the front. All right, you leave it off for now. So don't write if at the front. So I'm gonna use the original. I'm just gonna jump right in. So I'm gonna leave off if, and I'm just gonna start with this. You are the Scarlett Johansson. You are the ScarJo. And again, Scarlett, I apologize, just saving time. You are the ScarJo, comma. Now, do we write the word then? No. All right, that's the other part that gets changed. You don't write the word then. Where the word then would be, you put this new thing called if and only if. If and only if, which that's like, I think it's like 11 characters or so, and that's too much for us math people, so we got a cool abbreviation for that. We say IFF. Now that's not a righto, that is on purpose, that's intentional. An if with an extra F means if and only if, and that's now an official abbreviation you can use in this class. And then you put the back part or the conclusion on. If and only if you play the Black Widow in the Avengers movie. So if and only if you play the BW in the Avengers movies. All right. Questions so far? Man, we're rocking and rolling, man. It's taking a lot of time, though. I'm going to have to pick up the pace. So I think after this, I give you a chance to do a Miss Cook one. And again, this is not on your guided notes. Those of you who have your guided notes, you can turn them on the side. There's a little spot right here where you can do the Miss Cook example. For those of you at home reading this, it says, if you are the principal of Charlestown High School, comma, then you are the Miss Amy Cook. So write that down if you need to. What would be the truth value of that statement? Now, some of y'all, if you're online students, you might not know. I hope you've probably gotten emails from her and everything. But yes, Miss Amy Cook is our principal, so the truth value of that would be true. And now we want to do the converse. Again, that's where we take the hypothesis and the converse and we switch them. All right? So the converse of that would be if you are the Miss Amy Cook, if you are the Miss Amy Cook, comma, then you are the principal of Charlestown High School. Then you are the principal of, we'll just say CHS. And is that statement, what's its truth value? TV, what is its truth value? And again, boom, it's true as well. So we've got a conditional that's true, and then we've got a converse that's also true. That means it is eligible to be mashed together into a biconditional statement. And again, you can use the original conditional or you can use the converse as order. It doesn't matter, but please follow that format and take a second and write yourself a biconditional. Give yourself a little practice. All right. Okay, I hope y'all all did that. And if you remember what I told you to do, again, I'm going to use the original. And hope you remembered the format of a biconditional. You leave off the word if, so I'm going to scribble it out. I'm going to start off with, you are the principal. Now remember, if you wanted to use the converse, that works too, because remember, bi means it both ways. Either way is fine. So I'm going to use this one. You are the principal of CHS, abbreviate a little bit, if and only if. So I'm going to use that little fancy little thing we learned, IFF. If and only if you are the Miss Amy Cook. All right, I hope that's what everybody had on their paper. We're going to wrap this up. We're going to do, at the bottom of the guided notes, there's a few questions. Again, if you don't have this, I'm going to hold it up to the screen. You can pause it and write it down if you can see it. And then I'm going to rip through these. I hope everybody's pulled this up. But here you go. Here it is. It looks like it's about the best I'm going to get it right there. So if you want to hit pause, boop, boop, boop. All right. So hopefully you hit pause and you can copy it down on your paper. But I got a few questions. We'll just pull ourselves up a blank screen here. The first 5 say why this is not an acceptable definition. The first one says, an automobile is a motorized vehicle with 4 wheels. Well, we had a young lady who blew this lesson away, 6th period. She was. I think she almost got all of these right. She pointed out that definition is not reversible. So if I say, if it's an automobile, then it is a motorized vehicle with four wheels, and you try to reverse that and say if it's a motorized vehicle with four wheels, then it's an automobile. Well, people came up with all kinds of definite things. Oh no, a four-wheeler, that's not an automobile, and it's motorized, has four wheels. And then some people said golf cart, So people came up with a lot of examples why that definition is not reversible. So that's why that one's good. The next one, number 9, says a circle is a shape that is round. That's true, but that's not a good definition. Because some people are throwing out, well, an oval's round, my basketball is round. And somebody, well, basketball is a circle. Well, we're going to learn later, basketball is not a circle. You might say it's circular. We're going to learn later that's called a sphere, all right? So, there's a lot of things that are round that are not circles, is what I'm trying to say. So on that one, that messes up the second component of a good definition is not precise, right? Not precise. Okay, number 3, this one gets a little hairy. It says the median of a set of numbers is larger than the smallest number in the set and smaller than the largest number in the set. Well, again, man, some people thought way hard on this one, and they're saying, oh, what if all the numbers were the same? And then, so there was one example right there. If your set of numbers is 5, 5, 5, 5, 5, then the median is 5, which is not smaller than the largest number, and it's not bigger than the smallest number. So that was a good example. Also, you all know it's got to be the number right in the middle. Median means middle, and it can't just be real close over here to the largest, and it can't be real close over here to the smallest. It's got to be the dead middle center. All right. And number 11, this was kind of a goofy one. It says cricket is a game played on a large field with a ball and a bat. When I think of a large field and a ball and a bat, I do not think of cricket. I think of baseball. Got the Indians tie on today. Yeah, my third favorite baseball team right here, the Indians. Yeah. So I'm not a big baseball fan. I love collecting baseball cards from the 70s, but I'm not a big baseball fan anymore. But I like my Indians. I like my Pirates. I like my Orioles. And my Pirates and my Orioles, last I looked, they're not doing so good. Thank goodness for hockey, right? Yeah. Okay. Go Bruins. Yeah. Now, okay. So, yeah, baseball would fit that definition too. And so cricket, that's not a good definition for cricket. All right. So then the last one says, number 12, the last one in that section says, a rectangle is a very pleasing shape with smooth sides and very rigid corners. All right. So the fact that it said very pleasing, who knows what's very pleasing to people? I mean, that's kind of vague right there, not very precise. And then smooth sides and very rigid corners. Well, a triangle has smooth sides and very rigid corners, and obviously a triangle is not a rectangle. So that's, again, not very precise. Okay, then we got these things, another fake word called piggles, not piggies. Some people thought that was piggies. It's piggles. You got these guys down here who are piggles, and these guys over here are not piggles. Then we had 3 examples of guys wanting to be piggles, and did any of them make it? Well, number 13, he made it, and he's definitely a piggle. 13 was yes. 14 would be no, and the reason is because he's got that opening. If you looked at the piggles, none of the piggles had openings, so he's not a piggle. And then 15, what our culture considers a heart shape is it would be a piggle because it's closed. And then some people are saying, Mr. Metcalfe, look at the non-piggles. You got that 8 shape and you got that like weird hourglass shape. They're closed. Yep, but they have 2 sections as opposed to these piggles only have 1 section, so that's why they're non-piggles. All right, man, there went the first lesson. Wow, that took, this is going to be a long lesson, guys. So that took care of that. And remember, it's 2 lessons in one, so you want to break it into 2. The homework's broken into 2, so yeah, if you want to say, stop there, man, I had enough of Mr. Metcalfe, go ahead and turn it off. Watch some TV if your parents are down with that. You watch some TV or play some sports, and that'd be even better, man. Go outside, shoot some hoops, hit some tennis, man. Back in the day, okay. And then we're gonna jump into the new lesson, which is one of my favorites. All right, so we're moving on as promised. I'm gonna real quick I'm gonna real quick. I'm gonna calibrate my board, and you can pause it right here. Fast forward right through this, man, because this is just me recalibrating this Ethel here. Ethel, she's old and she's ready to be put out to pasture, but we aren't quite there yet. Okay, man, look at all this. You might want to hit pause if you don't have the guided notes, which there's guided notes for this, man. Look at all that. Guided notes, the main reason for them is to save you some writing. So I'm going to hold this up and, I don't know, do what you got to do. If you don't have this, if you didn't print it out, or if you didn't feel like putting a photo, it's in Google Classroom. Bam. So there it is. I'm going to rip through this. You don't have to write all this stuff. Oh my goodness, please don't write it all if you didn't do that with printing it out. But we're going to move on to deductive reasoning. And as promised, we talked about inductive. Remember, inductive was all about patterns, 2, 4, 6, 8, that kind of stuff. And we talked about how sometimes patterns don't hold out, so you can't use it, in a court of law. You don't want to use inductive reasoning because we've proven that the pattern doesn't always hold up. Deductive reasoning does. All right, so deductive reasoning, also known as logical reasoning. That's probably the last time you'll hear me say logical reasoning, because I'm going to say what the cool kids say, deductive reasoning. It's a type of reasoning that uses facts, rules, definitions, and properties to reach logical conclusions. So we're using facts, we're using rules, formulas, definitions, and then always a good dose of logic kicks in to come to a logical conclusion. So when you use deductive reasoning, it's going to lead to the correct answer, because you're not, it's not anybody's opinion or anything like that. It's not a pattern that you're hoping is going to continue. This is facts, rules. Yeah. Okay. So real quick recap. So facts, rules, logic, that's deductive. That's the new one we're talking about today. And just remember, inductive, that's when we used patterns. All right, so let's see what these people are using in these examples. Okay, so is it inductive or deductive? The first one says, every time Katie has worn her favorite socks to a softball game, she has gotten at least one hit. Katie is wearing her favorite socks to a game tonight, so she concludes that she's going to get at least one hit. So she's got her lucky socks or her favorite socks, and she's saying, well, I got them on tonight, so I'm going to get at least one hit. Is she using inductive or deductive? All right, I hope you all know when you have favorite socks or lucky rituals you do before each game, you might notice the pattern, like, man, when I wear these socks, I usually do well or whatever. But that's a pattern. That's inductive. All right. Hopefully everybody had inductive for that one. Okay. If John is late making his car insurance payment, he will be assessed a late fee of $50. John's payment is late this month, so he concludes that he will be assessed the late fee of $50. Is he using inductive or deductive reasoning? Okay, well, again, I hope you went with deductive this time, because it's not just a pattern that, it seems like when I'm late I get a fee. No, it's a rule. I mean, that's the rule right there. I mean, you're late with your payment, you're going to get a fee. That's not a pattern that happens. That's a rule. So yeah, that would be deductive. Okay, number 3. All the signature items on a restaurant's menu are noted with a special symbol. All right, so signature items. Sometimes students say, what's a signature item? Certain restaurants are known for certain things, like Hooters is known for wings, KFC, chicken, right? I mean, so sometimes they have a signature item, and on this particular restaurant's menu, they have like a special symbol. I think I got it down right here. Yeah, they use this @ sign as their next to their signature item. So, all right, so that's what a signature item is. It just means what a restaurant's known for, right? Okay, so Kevin orders a menu item that has the symbol next to it. So he concludes that the menu item that he has ordered is a signature item. So is he using inductive or deductive? I hope you know that's probably the trickiest one in the batch, but it is deductive. All right, that symbol is like it's like defining what the signature items are. So they don't just randomly put it on there to make the menu look pretty. They only put it next to the items that are, by definition, their signature items. So that was deductive. Okay, good job. That was a tough one. That was the hardest one in the batch, in my opinion. Okay. Oh, I like this one. Number 4. None of the students who ride Raul's bus own a car. So picture Raul. He's sitting on the bus. He's looking around at all his bus mates, and he's realizing, hey, none of us own a car. We don't own our own car. So then his friend Erica, he notices she also rides a bus to school. So he concludes that Erica does not own a car. All right. So did he use inductive or deductive? Well, he used inductive. He's noticing a pattern. All the guys or people on my bus do not own a car, right? So there's not some rule or law that says if you're on Raul's bus or any bus that you can't own a car. I mean, their car might be in the shop, or they just don't want to drive it to school, whatever. So the fact that he's taking that pattern of the people on his bus not owning a car, and he's hoping it'll carry over onto Erica's bus. So maybe it does, but maybe it doesn't. So that would be inductive reasoning. All right. Then we got a vocab word. Real quick, if you're in your guided notes right there's the word valid. You'll like this definition. It's one of the shortest definitions in the history of writing definitions in high school. The word is valid. It just means it's logically correct. Like if somebody says, let's see, Mr. Metcalfe, you're dumb because you have a silent E on the end of your name. That would not be like valid, all right? That's not logically correct that I'm dumb because I have a silent E on the end of my name. That's weird. I mean, so that doesn't make sense logically. That would be invalid to say somebody's dumb based on how their name is spelled. All right. Now, if somebody misspells their name a lot, you might say, okay, all right, but that doesn't make it. Okay, moving on. Law of detachment. Oh my goodness. Now, we are getting into the juicy part right here. There's 2 different laws in deductive reasoning. There's probably others, but we in high school geometry, we only talk about 2 of them. The first one is the law of detachment. All right, blah, blah, blah. There's the math definition. Let's go ahead and go over it. It's a valid form of deductive reasoning that states if something is, this definition is not too bad. If something is true in general, it will also be true for specific examples. What does that mean in normal people talk, Mr. Metcalfe? It means if something is true for like if I said, and bear with me, just say, if I said everybody at Charlestown High School has great hair, all right? Okay, just go with that. Everybody at Charlestown has great hair. And then I pick a specific person that goes to Charlestown High School. Like I say, let's say, make up a kid like Fred Stanley, we'll say. Hopefully nobody in Charlestown High School's name's Fred Stanley. But if Fred Stanley was a student here, then we could say, well, if everybody in Charlestown High School has good hair and Fred Stanley goes to Charlestown High School, then the law of detachment would say, well, Fred Stanley has good hair too. I mean, if it's true for a whole group or in general, then it's true for specific examples. Does that make sense? Like, to me, that makes sense. Like, if you said, let's see, every even number in the world is divisible by 2. All right, so every even number in the world is divisible by 2. And I said, what about the number 8? So if I get specific, well, 8's an even number, so then it would also be divisible by 2. If it's true for all even numbers, and 8 is a specific example of an even number, then it's true for 8, right? Y'all feeling that? We're going to do some examples, make sure. Okay, in words, and this is not as important, it's if P, and then that's an arrow, Q. So if P, then Q is a true statement. If the P part is true, then the Q part is true. That's what the law of detachment is saying. If it's true for all these people, and then Q is one of those people, it's true for Q as well. All right. So I like the more down-to-earth examples better. All right. So given. Oh, okay. Now, this might be the first time given has popped up in geometry class. Given means what I'm about to say is fact. It's absolute truth. So, and even if you say, well, I'm going to argue with that because I know this one thing and it means, no. In geometry class, when I say the word given, whatever comes after it is absolutely true in this case, all right? So don't say, well, I don't agree with what you just said. No, that's not the time or the place. Now, if I make a conclusion later on and you want to argue with that, that's okay. But the given, when I give you something in geometry class, and I will indicate it by saying with the word given, you just accept that. All right, that's the absolute fact in this problem. So, and then some people would try to argue with me right off this. If I didn't have that word given in front, they'd try to argue. Watch, because look what this statement says. Given, if a car is out of gas, then it will not start. All right? So, boom, that's it. No, we're not talking electric cars and I got a windmill car at home. No. All right? It says given, so that's the fact. If a car is out of gas, then it will not start. Okay. Then the second part of it says, it's still under the given, so this is another absolute fact. Sarah's car is out of gas. Okay. So what valid conclusion could we come to? Like, if a car is out of gas, it will not start. And then I get specific and say, hey, Sarah's car is out of gas. What could you come up with? Boom. Sarah's car won't start. If that's true for all cars, then it's going to be true for Sarah's car. All right, so valid conclusion would be Sarah's car will not start. Okay. Boom, there you go. Now, so does that make sense? If it's true for the general group, then it's true for the specific examples. All right. Ooh, okay, here we go. We're going to tie it to geometry, man. They always do this when we get these logic lessons, and then they're juicy and fun, and we're interesting examples. Then boom, they say, okay, let's slip some geometry in there, and then it's usually a lame example, like this one. Okay, given, if two angles form a linear pair, then their non-common sides are opposite rays. Okay, so, and that's well, not only is it true because it says given, it's just true, all right? If two angles form a linear pair, then their non-common sides are opposite rays. So here's a linear pair. Whoop. There's your line. I just made it into a pair. Okay, so you got your linear pair. Then their non-common sides are opposite rays. So here's their common side. That's the side they share. So their non-common sides do make opposite rays. Absolutely. So that's true in general. Then they get specific. Angle AED and angle AEB form a linear pair. So let's just call this guy AEB. And then angle oops. I did that wrong, didn't I? AEB and AED. Yeah, I need to put the... All right, we'll edit this out later. Yeah, we'll edit this out later in post-production, I think they call it. So yeah, AED and AEB are a linear pair. My bad. So then it says AED. Is this a valid conclusion? Ray ED and ray EB are opposite rays. Well, there's ED and there's EB. They definitely form opposite rays. So what they did is they went in general, any linear pair, the non-common sides are going to make opposite rays. Then they got specific and gave you two specific examples that make a linear pair, and boom, sure enough, their rays did exactly what they thought. Man, this video is going to take a while to load up on YouTube tonight. Man, thank you for hanging in there. If you want to break this down into two parts, I get it. Okay. So yes, that would be a valid conclusion. Yes. All right, here's another one. Now we're back to the more interesting ones. If Mika goes to the beach, she will wear sunscreen. All right, so if Mika goes to the beach, boom, she wears sunscreen. And then it says Mika is wearing sunscreen. So those are absolute facts because they are under the given. All right. So if Mika goes to the beach, she'll wear sunscreen. She is wearing sunscreen. So is this a valid conclusion? Mika is at the beach. All right. What do you think on that one? That's a good one. I like this one. Give you a few seconds to think about it. And I hope you said, no, it's not a valid conclusion. You're like, what? It says if she's, at the beach, she's wearing sunscreen. Well, the law of detachment only works in the order it's given to you. So they said, if she goes to the beach, she'll wear sunscreen. They are saying Mika is wearing sunscreen, therefore she's at the beach. They're trying to go in reverse order. And the law of detachment, if you need to make a note here, law of detachment does not work in reverse. All right? So I'm going to write that. Law of, and I'm not going to write out detachment. I'm going to write law of detach does not work in reverse. Does not work in reverse. And here's why. Just because she's wearing sunscreen does not put her at the beach. There's other reasons she could be wearing sunscreen. She could be at the lake. She could be at a tennis match. She could just be playing frisbee outside, so she wants to wear some sunscreen. So when she goes to the beach, she definitely wears sunscreen. But when she's wearing sunscreen, that doesn't mean she's definitely at the beach. See, it doesn't go in reverse, all right? It could. I mean, she could be at the beach, but we don't know for sure based on this information. So that is not a valid conclusion. All right. Back to the geometry part. Hey, I love geometry. I just don't like when they take a lesson and try to twist it so that they can get some geometry in there. But here we go. If 3 points are non-collinear, they determine a plane. That's true. We learned if you got 3 points and they're not all in a line, they can be connected by a plane. One plane. That's it. Points A, B, and C lie in plane G. So would this be a valid conclusion? A, B, and C are non-collinear. All right. So they're getting specific. All we know about A, B, and C is that they're in plane G. So here we draw a little plane, and A, B, and C, we know they're on there, but does that guarantee that they're not collinear? Again, I believe they're trying to use this in reverse, all right? So they're saying non-collinear, you make a plane. So if they said A, B, and C are non-collinear, we could say they're on a plane, but they're saying they're on a plane, therefore it's non-collinear. So again, that's a no good. They're trying to use the law of detachment in reverse. So that's not valid. All right? You see what I'm saying? 3 points make a plane. A, B, and C make a plane. Oh, I'm sorry. Woo! I'm sorry. Better edit this out. 3 points are non-collinear. They make a plane. And then they're saying 3 points make a plane, so then they're trying to go back to non-collinear. See how they switched the order up on you? That's why it's not valid. All right, they cannot change the order. Law of detachment is not guaranteed to work in reverse. All right, moving on. We got a fourth one. I like back to normal, back to the real world. Given if a student. I should have the word any. If any student turns in a permission slip, then the student can go on a field trip. So that's in general. If a student turns in his permission slip, boom, you're going on the field trip. Felipe turned in his permission slip. Would this be a valid conclusion? Felipe can go on the field trip. So here's the deal. The order is student turns in his student turns in his permission slip, you go on a field trip. Then they get specific. Did they follow the same order? Felipe turned in his permission slip. Can Felipe go on the field trip? Boom. Yes, that is definitely valid. That's a valid one. Okay. Judge conclusions using Venn diagrams. So if you got the guided notes, you notice these Venn diagrams are not drawn. We're ripping through this. We're down here. I drew the Venn diagram of what they said. It says, given, if a primate is an ape, then it doesn't have a tail. So you got ape over here, you got tails over here, and they don't overlap. Some people say, well, that's not a Venn diagram then. Then I say, yes, it is. Yeah, all you need is some bubbles and stuff. You got a Venn diagram, basically. All right. Some people think, because every time you see a Venn diagram, they do overlap. Usually you have something like that and something like that. They don't have to. You don't have to draw your Venn diagram that way. That's just how they usually look. And these are mutually exclusive. So if you're an ape, you don't have a tail. If you have a tail, you're not an ape. All right. And then there's other primates. There might be primates out here that are not apes and don't have tails, or So that's how that Venn diagram works. So here's what we know. Coco is a primate. So what that means is Coco is in this box somewhere, because these are all the primates in this box. Coco is a primate who does not have a tail. All right. So we know Coco's not in the tail bubble, because, she doesn't have a tail, or he. I don't know if Coco is a boy or a girl. So Coco is a primate with no tail. Can we come to the conclusion that Coco is an ape? So she's a primate. She has no tail. Does that make her an ape? The answer would be no. All right, so all we know from this Venn diagram is Coco is in this box, but not in this bubble. So Coco could be in the ape bubble, but Coco could be over here where she's not an ape or she doesn't have a tail. And I don't know what that would be. I mean, you biology people might know there's some kind of primate that is not an ape and doesn't have a tail and is not Coco, or is Coco, I guess. So there you go on that one. Does that make sense? All right, let's move on. Here's another Venn diagram. This one you'll like. This one's much easier. This one says, if a figure is a square, then it is a polygon. Okay. If a figure is a square, then it is a polygon. So here's the whole square family right here. They're in the polygon box, because it says if you're a square, then you got to be a polygon. So there's no squares out here. Nope. If you're a square, you're in that polygon box. All right. Then they say figure A is a square. So I put an A in the square bubble. Can we come to this conclusion? Figure A is a polygon. Absolutely. Because all squares are polygons and A is a square. They told us that. So if you're a square, then you have to be a polygon. That is definitely valid. All right. Moving right along. Y'all staying with me? Ooh. Now, the second law in deductive reasoning is called the law of syllogism. All right, I'm going to give you a chance there's a lot of stuff to write here. Law of syllogism. It's another type of deductive reasoning that allows you to state a conclusion from two conditional statements. All right, you need two conditional statements for the law of syllogism to work. And the conclusion of one statement is the hypothesis of the other statement. So you have to have two conditional statements, and the conclusion of one has to be the same as the hypothesis of the other one. And I always say, so you got this situation, and this, I'm going to say it in a kind of a dun-dun-dun-dun style, and I think you'll feel it, because I'm going to do this pattern over and over. If P, then Q, and Q, then R, then your conclusion is P, then R. So look what the overlap is. This one's got a Q in it, that one's got a Q in it. So his conclusion matches up with his hypothesis. So what happens is that, I call it a bridge. You use the Q as the bridge to go from P over to R. Boom to boom. You can jump over the Q because it overlaps. It's true for the one and it's true for the other. So you're kind of jumping over it. that is very similar to one of the properties you learned probably late in elementary school or maybe early middle school. It's acting like the blank property. So if you think you know which property that is, there was a property, I know your teacher taught you this. They said if A equals B and B equals C, then A equals C. That was one of your properties back in the day, man. I hope you all remember that one. I'm probably going to wait and reveal that later on. All right? Okay, so you need the two statements, the two conditional statements, and the conclusion of one has to be the same thing as the hypothesis of the other one, and that's the overlap or the bridge, and those two that you have in common, you jump over them from this to this, like from A to C, where that whole A equals B and B equals C thing. All right? So we got a couple of good ones here. Example 1 says, if you get a job, then you will earn money. If you earn money, then you will buy a car. Do we have two conditional statements with a piece that repeats? We absolutely do. Look at that. If you get a job, then you will earn money. You will earn money is then said again in the next one. So that is the repeating piece that we're going to jump over. So a valid conclusion would be, if you get a job, then you will buy a car. Jumping over this overlap, all right? So if you get a job, whoop, you can buy a car. You will buy a car in this one, all right? So that would be your valid conclusion. And yeah, let you write that out. Ooh, and here's one of my favorites. All right, given. Batgirl is a superhero librarian, and then superhero librarians are hot with two T's. All right, that's that lingo that kids like to use. Hot with two T's. All right. So, we got two statements here, and is there an overlap? We do have two statements. We got Batgirl is a superhero librarian, and then the second one says superhero librarians are hot, and we do have an overlap. The superhero librarian part is overlapping. So what would be the valid conclusion if we use that as the bridge? The overlap is the bridge. We could say Batgirl is hot. All right? Batgirl is hot. All right? Any questions on that, man? If you got them, send them to me. Please watch these videos. Well, I guess if you're not watching the video, it doesn't do me good to tell you to watch the video. So, yeah, erase that. All right, moving on. We're almost done, man. This is screen 6 of 7. And I think the last screen is literally just some homework problems. And, man, oh, my goodness, it is late. All right, standardized test example. Determine which statement follows logically from the given statement. Statement 1, if Flynn finishes his homework, he will go out with his friends. If Flynn goes out with his friends, he will go to the movies. So, we got 4 choices here. And the last one says there's no valid conclusion. You can't make a valid conclusion for that. So, let's take a look at those statements again. Obviously, a hint, it's going to probably be, if it works, it's probably going to be law of detachment or law of syllogism. So, you can look, and this doesn't seem to say like it's going from the general to the specific. It seems like it's very specific already. You know, Flynn. That's my son, by the way, is Flynn. It seems very specific right from the start. It doesn't say, like, if people do their homework, then they're going to go with... It just says it's specific. So I think we can get rid of the detachment one because it's already specific. So the second thing is, do we have 2 statements? Boom, we do. Statement 1, statement 2. And 2, do they have an overlap? Well, let's take a look. He will go out with his friends is the conclusion of the first statement, and go out with friends is the hypothesis of the second statement. So we do have that overlap, that bridge. And so I'm going to go from the first part, Flynn finishes his homework, and I'm going to jump across the overlap to, if Flynn finishes homework, he will go to the movies. So is that one of our choices? If he finishes his homework, oh, look at it, not A doesn't work. If he finishes his homework, he will go to the movies. That one looks pretty good, so we're going to put a little mark by that, but you always want to check the other ones. And then there's something about he does not go to the movies. He will not go out with his friends. We don't know about that. And then there's no valid conclusion. Well, we found one, so it's not that. So B, hopefully everybody had B for that one. And man, all right, we gotta move. I'm supposed to be home like in 2 minutes, and I got a 30-minute drive, so I ain't gonna make it, right? All right, so apply laws of deductive reasoning. Okay, so this is kind of like a recap, all right? So now we're going back to either syllogism or detachment. Either one is fair game in this one. So draw a valid conclusion from the given statements, if possible, and tell if you use the law of detachment or the law of syllogism. If no conclusion can be reached, write no conclusion, explain your reasoning. All right, so given. Remember, there's a given, so this is absolute fact since it says given. If it snows more than 5 inches, school will be closed. All right, so if it snows, that's whatever the school district we're talking about, that's their thing. If it snows 5 inches, they're going to close school. All right. On January 27th, it snows 7 inches. Okay. So what kind of conclusion can we make? So they got specific. They went in general, ever 5 inches or more snow, we're going to close school. And then they got very specific. On January 27th, it snows 7 inches. So I think our valid conclusion would be on January 27th, school is closed. Does that make sense? So conclusion would be on Jan 27, school is closed. All right. And did we already said we didn't use detach. Oh, wait, no, that was on this one. On this one, what did we use? Let's see. It's not syllogism. We do have the two statements, but we don't have the overlap in them. We have general and then specific. So when we have general to specific, that's the law of detach. And man, we're going to wrap this up. The last one says, another superhero one. You probably picked up on it by now that I like to read comic books. I collect them mostly, but I like to read them too. And then given, Superman wears a red cape. People that wear red capes are soft. So, can we make a conclusion from that? Well, we kind of started off with specific, and then we sort of went a little bit to general. Law of detachment kind of goes the opposite way, so I think we might want to look at syllogism. So do we have two statements with an overlap? Well, we got Superman wears a red cape. Wearing red capes is soft, so we do have the two, and there is an overlap. We got wears red capes. So our conclusion would be Superman jumping over wearing red capes to being soft. So our conclusion would be Superman is soft. And yeah, if you're a big Superman fan, I'm sorry. He's one of my least favorite superheroes because he's just, too powerful. He can, only one thing hurts him. That's kryptonite. And I don't know about you. I haven't seen too much kryptonite lying around. So he's in pretty good shape here on Earth, I would think. So what did we just use? Did we use detachment or syllogism? Well, we did that bridge thing where we had the overlap. And when you do that, that's the law of syllogism. All right. Man, I hope you survived all that. I hope this uploads. What does it say on time? Ooh! Hour and 8 minutes, man. Sorry about that, but it's 2 juicy lessons in one. Good luck. Break it up if you need to, and I'll see you next time.